In today's video, we're going to be talking about the mathematics of refraction. If you remember in the previous lesson, we talked about how you could determine the way a light ray would bend when it enters a new medium. And there's really no numerical value to that bending. We really had no idea what the angle was that was being created by that ray of light. Well, today we're going to change that, and we're going to add a mathematical component using basically something called Snell's law. So after watching today's video, we should be able to do a couple things. One, you should be able to determine the angle of refraction. Actually give me a numerical value for that angle. And the way you're going to do that is you're going to use something called Snell's law. And you should be able to still, again, draw ray tracing diagrams. Again, in the previous video, I had talked about a mnemonic device where I said, if you use this term FST, which basically stands of a light ray going from a fast medium, that's what the F is for, into a slow medium, the ray of light is going to go towards, that's what the T is for, towards the normal line. Whereas if you're going from a slow to a fast one, we use the mnemonic device SFA, where it's S for slow, F to fast, and then A is away from the normal. Okay, and I'll again be using these two guys in this video to show you examples of using Snell's law along with kind of checking our answers by using these mnemonic devices. Okay, so let's get right into it. Again, a reminder, refraction is the bending of the path of a light wave as it passes across the boundary separating two media. Okay, so in this picture on the right here is the incident ray. This is the ray traveling in air towards this air-water boundary. So I mean, you can pretend this is a pond or whatever the case may be, but this light ray is traveling towards the water. It hits the water, and what ends up happening is this light ray refracts or gets bent as it enters into the water. Okay, and what we're interested in learning about today is talking about this angle of incidence. That's what theta I stands for, and this angle of refraction. That's what theta R stands for. Okay, and the incident ray is the ray that's coming in to hit the media, and then the refracted ray is the one that kind of continues on through to the new media once it strikes it. Okay, so how do we determine these angles? Okay, this angle, the angle of incidence, and the angle of refraction. Well, basically this slide is kind of just reiterating what I just said in the last slide. Basically that this theta I is the angle of incidence, and this theta R is the angle of refraction. So that's what this text is right here, basically, is it's going through the stuff that I just talked about in the previous slide. So I'm just going to move along. If you need a pause, be my guest. Here is how we're going to figure out a numerical value to these ray diagrams, if you will. We're going to use something called Snell's law, and I apologize, this is kind of a blurry picture, but this N sub I stands for the index of refraction. There it is. N sub I stands for the index of refraction of the incident medium. Okay, so this is that it could be for air, it could be for water, it could be for glass. It doesn't really matter. Whatever the light ray is traveling through, that's what that N is going to be. And that's going to typically be a value that I will give you. Sometimes you have to calculate it, but typically I will give you the index of refraction. Sine theta I is the angle at which the light ray is traveling in this or for the angle of incidence. Okay, so that's the angle at which it's traveling. And then N sub R is the index of refraction for the refractive medium, whatever the new light ray is traveling into. And then sine theta R is the angle at which that light ray is going to make. Now, I feel like I probably just made this more confusing than it really needs to be. This I don't think is that bad of an equation, and I think once we start to use it, you'll see this isn't so bad. So let's do some example problems and get a feel for what Snell's law really all entails. All right, let me change the pen colors here so that you guys can actually see what I'm writing, which is always useful. Okay, it says a ray of light in air is approaching the boundary with water at an angle of 52 degrees. Determine the angle of refraction of the light ray. Okay, as always, I recommend drawing the problem and kind of writing down your things that you know. Okay, so first, this ray of light is traveling in air. Okay, so we got some air here. And it's traveling in air, and it is headed towards this water down here. Okay, so it's in air headed towards the water, and it is making an angle of 52 degrees. Now, what is that angle really coming from? It's coming from this line called the normal. And I'm going to make that be a different color just so that you guys can clearly see that. The normal is just running perpendicular to the boundary. Let me extend this line down here this way. Okay, so this is, that red line represents the normal. So this light ray is traveling at an angle of 52 degrees, okay, and so that's right here, 52 degrees, okay. And what I'm wondering is, well, first, what is the N for air? What is the index of air? Well, that would be N equals 1, right? I give that to you right up here, okay. And what is the index for water? I'm just going to change pen colors here because I feel like that's so dark it's really hard to see. The index for water is N equals 1.33. Okay, so right away I can ask you guys, and you should be able to tell me pretty quickly, which medium will light travel faster in, air or water? Well, air it looks like, because it has a lower N value. Okay, so I'm thinking right off the bat, my mnemonic device of going from a fast medium, being air, into a slower medium, being water, I'm going to be using the word FST. So it's going to go fast to slow. And so what's this ray going to do when it enters into the water? It's going to bend towards the normal. Okay, so it's probably going to head this direction a little bit. It's going to have a little bit of a bend to it, okay? And instead of extending this way like a straight line, it's going to be bent towards the normal, okay? And what I'm wondering is, what the problem is asking is, what is this angle right here, okay? What is theta right there? Oops, theta. And it would be called theta r, angle of refraction. Okay, what is the angle of refraction in this problem? Okay, so how do we solve that? Well, we're going to use Snell's law to basically solve this problem. And I'm just going to quickly change colors one more time, just so you guys can kind of follow along with me. We'll use green. The N of air is going to be here, and then you have sine I equals N sub r, and then sine sub r. Okay. So what is the N of air? Well, the N of air is 1. Okay, 1. I mean, if you want to put all the zeros after it, you can, but it's really unnecessary. And then we have sine, and the angle was 52 degrees. Okay, sine of 52 degrees equals N. What is the N of water? Well, it's 1.33, right? That's given to us right there. And then the angle of refraction is what we're curious to learn about, okay? And so if you do this math and you solve for, oh, I should really have sine here, sorry about that. And I should have sine there, sorry about that. Sine of angle r, what is angle r going to actually equal? Well, if you throw this all on your calculator, you would find that theta sub r equals 36.2 degrees. Okay, so this angle right there would actually equal 36.2 degrees, and that's through using Snell's law. And according to our FST, is that actually kind of checking out? Is that making sense? And the answer is yes, because 36.2 degrees is much less than 52 degrees. So it is moving towards this red line, which is known as the normal. Okay, it's moving towards that red line, which is known as the normal. Let's do another example problem, and we'll get a better feel for this. It says a ray of light in air with an index of 1 is approaching the boundary with a layer of crown glass with an index of 1.52 at an angle of 42 degrees. Determine the angle of refraction of the light upon entering the crown glass and then upon leaving the crown glass. Okay, that's great. So this is going to be a little bit tougher problem, and the reason why I'm saying it's a little tougher is because we're going to have two parts to this, okay? I'm going to draw a box. And this box is going to represent, this is the glass. I'm going to take off the crown part. We're going to call it glass. And this has an N of 1.52. Okay? And we know that a ray of light is headed towards this crown glass, and this is air, right, out here. And the air has an N of 1. It's approaching the boundary of the layer crown glass at an angle of 42 degrees. Okay, I'm going to draw the normal with a different color here. I'm going to draw it with yellow. an angle of 42 degrees. Okay, that's 42 degrees right there. That's theta. Okay, I want to know when this ray of light enters the glass, how is it going to refract upon entering? Okay, so again, I'm going to use Snell's law to figure that out. Okay, so I'll do that part of the problem over here. All right, so we have the sine of theta sub I times ni equals sine of theta sub r and then nr. Okay. Now I did flip this around a little bit. I mean, you can have it in whatever order you want. If you would have n first and then sine, you certainly can. But the sine here is going to be 42 degrees. So we have sine 42 degrees times the n, which is 1, equals the sine of the angle, which is what we're trying to find out, times the n of the glass, which is 1.52. Okay? And again, if you just do the algebra and you manipulate this and throw it in your calculator, you would get a theta of 26.1 degrees. Okay? And so what it's basically saying is that when this light wave enters into this piece of glass, it's going to enter at such a way that the angle is going to be towards the normal. This angle right in here is going to actually be 26.1 degrees. Okay, and now let's see if that follows our mnemonic device that we talked about before. It's going from a fast medium, an F, to a slow medium, and so it's going to move towards the normal, right? And is it doing that? It started at 42 degrees from the normal, and now it's at 26.1 degrees to the normal. Did it move towards it? Absolutely, right? So that's great, all right? So that's part one, okay? Now it says that this light ray continues on its merry way until it hits this boundary here, okay? And the normal line, which I'll make yellow again, is still going to be perpendicular to the glass, okay? Still going to be perpendicular to the glass. And so this angle is still going to be 26.1 degrees. And that's why it's really key that you had to solve for that one first. So it's going to be 26.1 degrees because that's what we solved it for right here. Right? And it hits the glass and then this air boundary, which air has a n of 1. All right. What angle is this light ray going to come out of this box? And the answer is we again need to use Snell's law. Okay, so if we do that, maybe I'll do that up here just so I have some space. We have the sine of this angle, which is 26.1 degrees, times the n of glass, which is 1.52, equals the sine of theta here, okay, what is it going to come out as? And then what is the n of air? It is 1, which air is really nice to work with because 1 is such an easy number to deal with. Okay? And if you do the multiplication, or the algebra, I should say, here, you would find that it exits into the air at an angle of about 42 degrees if you round up. 42 degrees, which interestingly enough is the same angle at which it approached into the glass. Okay, so there you have it. Again, using Snell's law. So if you're still struggling with this, we'll definitely do some more examples in class. But that takes care of today's video. I will see you guys next time.